We're going to take a look at some more examples of these volumes of cross-section. And we're going to start off just by reviewing what we did yesterday. So yesterday we looked at cross-sections that were squares. So the area of a square is just s squared, and that's what goes inside your integral, s squared. And then we looked at triangles. So we had an isosceles right triangle. So these two legs were congruent, and of course it's a right triangle. So really it was just half of a square. So the area was just 1/2 and then the same area as a square. So that's what goes inside your integral, 1/2 s squared. And we didn't have anything like this yet, but what if the hypotenuse was the part of the triangle that touched the base? So that would be your s, the green part. In that situation, it's really 1/4 of a square. So your area would just be 1/4 s squared. And again, just to remind you what s is, you might have some function here, you might have some other function here. So we usually have a shaded region. Let's say that's your shaded region right there. And the s is either going to be perpendicular to the x-axis, so it might look something like this. So if your s looks like this, then it's just going to be top minus the bottom. So whatever the top function is, let's say if it was f and the bottom was g, then your s would just be f minus g. Or your s could be perpendicular to the y-axis. So if you had our shaded region like this, the right side could be x1, and maybe the left side is called x2. Your s could be something like this. So in this situation, your s would be equal to the right minus the left, so that would be x1 minus x2. So those are just some examples. Let's look at the next page. Next page, we have an example for rectangles. For this example, the s is the bottom of the rectangle, and then the height is usually a multiple of s, but your height could be anything. In this case, I'm just calling it w for width. So the area of a rectangle is just going to be your s, and that's the same s we had in every single example. And then the width is usually described. It could be 3 times your s, it could be half of your s, or it could just be some other function altogether. But the area of one rectangle is what gets plugged into your integral. We'll go to the next example. Again, we're just reviewing. This is semicircles. So if your s is the bottom of your semicircle, the part I just shaded with green, then the radius is really going to be from here to the outside. So the radius is really just going to be half of s. So I'm writing that right here. Your radius is 1/2 of your s. We know the area of a circle is just pi r squared, but this is a semicircle, so we put the 1/2 in front, and we can trade the r for 1/2 s. So you replace the r with 1/2 s, and after squaring it, you're going to get 1/4 s squared over here, 1/4 s squared, and then you have a 1/2 here, so you have half and a fourth, so you end up with 1/8. Of course, the pi, you just keep bringing down the pi. So you end up with pi over 8 s squared as your area of one slice. So the area of one slice is what goes in here. Doesn't matter what the shape is. We'll show that on the next page. Here's an example. You have one slice in the middle here, and that's what goes inside of your integral. It's just the area of one slice. And of course, we're going from x equals a to x equals b. So those are your bounds. That's your lower bound and your upper bound. And that's pretty much it. That will give you your volume. Okay, now we're going to look at a couple of new examples. Okay, for this example, they tell you exactly what the area is for one cross section. And each cross section is going to be perpendicular to the x-axis. So that's going to look something like this. But we're not actually going to use our s this time. We do know that our integral goes from -3 all the way to +3. So those are your bounds from -3 to +3. We don't even care what the functions are, because for this example, they've told us that the area of one slice is going to be 5 times x. So we're just going to put 5x in there, and we're done. So this is one of those examples that's so easy that it's hard. Everyone usually gets stuck. They don't know what to do. They try using their s because they always use the s. They get confused. So this is a really weird example that you usually don't see. And that's what we're taking a look at today. So something a little bit more tricky than usual. All right, let's go look at our last example. Number 2 is our last one. This is another really weird one. So on our homework today, we're still going to have all those easy ones, you know, with the squares and the rectangles and the semicircles and that kind of stuff. But we're also going to have a swimming pool example. So here's what it says. This is really weird. The example that we're looking at doesn't even tell you if the cross sections are perpendicular to the x-axis or perpendicular to the y-axis. The only thing it tells you is that we have a lake or a swimming pool. That's the shaded region. And it says that the depth is equal to 2y plus 8. Now what's important about that is the depth of the pond or the depth of the swimming pool depends on y. So let's look at an example. Let's say, for example, that y was equal to -1. And that's going to happen all the way across this line right here. When y equals -1, the depth is going to be this right here. It's going to be 2 times -1 plus 8. So that'll be 6. So we're getting a depth of 6 all across that line. So what that means is if the depth is always 6 along that line, you end up with a shape that's actually a rectangle. So that's kind of interesting. So what that means is that we have cross sections that are actually rectangles, and they're going to be perpendicular to the y-axis. So that's really tricky. I think this is more of a challenge problem. You're not going to see something this crazy very often. This is definitely a challenge kind of problem. You might get something a whole lot easier that just says that the cross sections are rectangles and they're perpendicular to the y-axis. That would be a much easier example. But let's go ahead and write down what the s is, and let's write down what the d is. The s is just going to be the right minus the left. So the right is this function here. Then we do minus. Then the left is going to be this function here. That's just 2/3 y squared. So that's going to be our s. The d, again, is kind of like the depth. That's going to be 2y plus 8. There we go, 2y plus 8. So now we're basically done. We are going to do the integral from y equals -3 all the way to y equals +3. So this will be a dy example. But our rectangles are going to be d times s. D times s. And this is our s and this is our d. So we can plug those in and we'll be done. All right, there's our integral there at the bottom. Remember, it's just a rectangle. So the area of that rectangle is just going to be s times d. So here's our s right here. And here's our d right here. And again, we're going from -3 all the way to +3. So our bounds go from -3 to +3. Again, this is a challenge example. You're not going to see many that are this difficult, but there is one on our homework. So we're going to try to do that one, see if we can get the right answer. And that's it.